Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the VLSI technology. In that we are discussing the CMOS processes, and today in this video we are going to talk about the 1990s technology. In the 1980s technology we had seen all of the basic steps for the formation of the CMOS chip. Right, so now we are going to analyze what was the difference between the 1980s technology and the 1990s technology. Obviously the 1990s technology is going to be better than the 1980s technology. So we are going to analyze how the 1990 technology was better, what all changes were there in the 1990s which made the chip fabrication better, and what all advantages we were having. So let's start our discussion. In the 1990, the main driving force was the digital logic electronics. We were moving towards the PCs, the personal computers, the telecommunication as well as the internet. The feature size was reduced from 0.8 micrometer which was there in the 1980s to 0.18 micrometer. The wafer size was increased for 150 mm to 300 mm. So 150 mm was present in the 1980s and we have actually doubled the wafer size in the 1990s. So this is a very big advantage. Now coming to the 1990s CMOS technology, what all changes were there? So we are going to see what all changes are there from the 1980s to the 1990s. First of all, we were having the epitaxial silicon layer. The epitaxial silicon layer was not deposited in the 1980s. So epitaxial layer was a highly pure layer which is deposited above the wafer, in which we can do all of the implantation of all of the components. So we were moving towards the epitaxial layer in the 1990s. After that we were moving towards the shallow trench isolation for the isolation formation instead of locos. We were moving towards the sidewall spacer for LDD as well as silicide. We were moving towards a polyside gate as well as local interconnection which were having the reduced resistance and improved device speed. So we were forming the interconnection with the materials which were having the less resistance and high device speed. So we were using tungsten silicide and the titanium silicide for that. After that, in the photolithography we were using G line, I line and deep UV. So I line was used at 365 nanometer and deep UV at 248 nanometer. We were using the positive photoresist and the steppers replaced the projection printers. Steppers were fully automated robotic type of materials which were using the photolithography process, and it was using a lot of the robots, and with the help of a lot of its arms, with the help of fully automated process, it is going to give me the photolithography process with the help of single type of structure. So now here the single hardware, that is a step tracker integrated system, is used for the full photolithography process, and this is the main change or the shift in the technology from the 1980s to 1990s. So track stepper integrated system were developed, and these track stepper integrated system were fully automated. There was less contamination inside it, there was less possibility of errors. Speed was increased for the photolithography because photolithography is a very highly timely required process. It requires a lot of time, and when it is fully automated the time requirement would be reduced, plus the contamination would be reduced. So this is how we are having a major shift in the technology in the 1990s. So we were using the plasma etching for the patterned etching. So plasma etching is also faster and more accurate. After that the wet etching is used for the blanket film stripping. Okay, after that we were using the vertical furnaces which were having the smaller footprint and the better contamination control. We were using the RTP systems with the help of post implantation annealing. With the help of silicide formation, it is going to give me faster and better process and the control on the thermal budget as well. So DC magnetron sputtering replaced the evaporation, right? So all of these are the changes. Now coming to the interconnection, we were having the multi-layer interconnection in the 1990s. We are going to see it with the help of pictures as well. The tungsten CVD and the CMP was used to form the plugs, and the titanium and the titanium nitride barrier and the adhesion layer is used for the tungsten. Titanium welding layer is used for the aluminium copper to reduce the contact resistance, and at last we were using the titanium nitride ARC, right? So After that we were using the borophosphosilicate glass, which was popularly used as a pre-metallic dielectric, and we were using the DCVD with the PE TEOS and the ozone TEOS for the STI, sidewall spacer PMD and IMD formation. The PE of this silane is used for the PMD barrier nitride layer deposition, dielectric ARC, and the PD of the nitride. The tungsten CMP was used to form the plug, and the dielectric CMP was used for the planarization. The cluster tools became very popular in the 1990s, and the single wafer processing system was there to improve the wafer to wafer uniformity control. Right, so we were using the single wafer processing system when we wanted a better wafer to wafer uniformity. The batch system was commonly employed in many non-critical processes for their high throughput. In the batch processing system, we were having a lot of wafers which are processed simultaneously, but in the single wafer process, as the name suggests, I am just processing single wafer at a time. So let's understand all of these things with the help of the pictures. So first of all, I am going to do the epitaxy layer deposition over the p-type of wafer. So after that, we are going to use the mask 1 for the N-well formation, right? After that, we will be having the N-well implantation. I hope you understand how we can make the N-well. So here we are skipping some basic steps, the photolithography steps that you now understand. I have talked about it enough of times, and now you understand how I am forming the N-well with the help of the photolithography and the positive photoresist over here, right? So here we have formed the N-well inside the p-type of epitaxial layer. After that, I will be using the mask 2 for the formation of p-well. So you can see this is the twin well process. Here I will be using the N-well as well as p-well in the p-type of epitaxial layer, and the p-well is formed with the help of boron ions, N-well was formed with the help of phosphorus ion. So you can see we can strip off the photoresist, we can strip off the nitride or the pad oxide layer, and this is how I will be having the p-well as well as the N-well. Right, after that we will be having the pad oxidation layer. Over that we can have the low pressure chemical vapor deposition for the nitride deposition, right? So after that we will be doing the shallow trench isolation. For the shallow trench isolation only, I have deposited the nitride first. So I will be using the shallow trench isolation mask, and with the help of photolithography I have made the trenches over here, right? So this is the trenches that is present here. We are going to etch out the nitride, pad oxide and the silicon to make this trench, right? After that we can fill it with the high density plasma chemical vapor deposition of the USG to fill out these trenches. And here, because here we had the trench, here the height would be this. Here we didn't had the trench, so height of the CVD of the USG layer would be more. So here we will be getting a rough surface. So to remove the rough surface, we are using the CMP to make it smooth. So we are doing the CMP of the USG layer, and we are stopping, or we are getting the endpoint as soon as we are reaching to the nitride. After that we are stripping off the nitride and the pad oxide, and we are going to clean it. So here you can see we have the shallow trench isolation of the USG layer. So this is how we have formed the isolation layers, right? After that we can have the Nchannel threshold voltage adjustment and implantation. So here we will be using the mask for it, and after that we will be using the phosphorus ions to implant the phosphorus in the p-well, right? So after that we will be having the p-channel VT adjustment implantation. Again I will be using a mask, and here I will be implanting with the boron, right? And after that we will be having the gate oxidation, and here I will be having a very thin gate oxide layer. Over that we will be having the low pressure chemical vapor deposition of the polysilicon layer. After that I will be using the gate and the local interconnection mask, like in the previous case in the 1980s technology I used, and here I will be forming the gate oxide, right? Here I have the gate oxide, polysilicon, over that I have the photoresist. With the help of mask I have etched out the photoresist and the polysilicon over this area, right? Now I will be removing the photoresist, and after that I will be using the N-channel lightly doped drain mask. So here with the help of N-channel lightly doped drain mask, I am going to dope this channel or the p-well with the help of the arsenic ions. So here I use the arsenic ions to dope and to make the N type of region or N type of source and drain over here, right? So after that I am choosing the P channel LDD mask, and after the alignment, exposure, and with the help of implantation with BF2 ions, I have the P type of source and drain region over here, right? After that we will be forming the sidewall spacer, right? The sidewall spacer are formed here, right? So here we will be having the sidewall spacer with the help of nitride. Here this is the gate oxide, over that we have polysilicon, and here we will be having the sidewall spacer. In both N type of LDD as well as P type of LDD we have the sidewall spacer, right? After that we will be having the N channel source and drain formation, right? So you can see here we will be having the N channel source and drain implantation with the help of phosphorus ions. We will be having the N channel source and drain implantation. Here we will be having the lightly doped drain implantation. After that I will be using the P channel source and drain mask, and with the help of it I will be using the boron ions, and I will be doping it with P type of boron atoms, right? Here I will be having P type of source and drain. After that I will be using the titanium silicide process. You can see over here we have the sidewall spacer, over which I will be covering it with the titanium first, then I will be having the reaction of the titanium with the silicon over here to the formation of the titanium silicide. Okay, here and here we have formed the titanium silicide, and then we are going to remove the excess or the bulk of the titanium that is present over here. So after that we have the titanium self-aligned silicide process. You can see over here, first of all we have the titanium deposition, then the titanium silicide formation, right? So this is the RTP of silicide alloying. We are doing the RTP for the silicide formation, and then we are going to strip off the unreacted titanium or the excess titanium, and this is how we will be having the titanium silicide present over here. So after that we will be having the borophosphosilicate glass deposition as well as the reflow. So this is how we will be having the deposition of the borophosphosilicate glass. The reflow is done because here you can see this is a rough surface. To make it smooth I will be having the reflow process. And after that we will be using the 10th mask for the contact hole formation. So you can see the contact holes are made over here. Wherever I want the contact with the N type source and drain or P type source and drain, I will be making the contact hole etching. So after that we are going to fill it with the titanium and tungsten. So first of all we are going to have the etching, and then we are having filling of this surface with the tungsten, and after that we will be having the contact hole etch and the BPSG etching. So you can see over here we have the titanium layer, over that we have this tungsten layer, and after that we have the titanium nitride layer. So we have the ARC layer as well. So this is how we will be having the aluminium copper layer in between the titanium and the titanium nitride, which is going to give me second metallization layer. After that this is how we are going to have the metal 1 interconnect mask, and with the help of metal 1 interconnect mask I am going to do the metal etching. So here with the help of aluminium copper alloy etching I am going to make the trenches over here, right? So with the help of PETOS USG deposition, first of all I am going to deposit USG, then etching out, and then deposition, and then CMP. So this is how I will be getting a planar deposition of the USG layer. So this is my IMD layer. This is called the IMD layer. After that I will be using the 12th mask for the via 1 host generation. So you can see we are having the via etch process over here. We are going to etch out the USG layer over here, and this is how the USG layer have made trenches over here. After that we are going to fill it with the metals. The tungsten is filled over here, the metal 2, that is aluminium copper alloy, is filled over here, and we will be having some coverings also with the titanium and the titanium nitride of course. And then we are going to have the metal 2 interconnect. We are using a mask 13 for the metal 2 interconnect, and then we are going to etch out the metal 2. Here we have, you can see with the help of the mask 13 we have etched out the metal 2, that is aluminium copper. And now again with the help of the deposition of USG, this is the IMD2 layer, we have deposited the USG layer. We can use the mask 14, that is the wire 2 mask, and then we can have the trench that is formed over here. So wire 2 etching is done and we are going to etch out the USG layer, and it is reaching up to this layer, titanium nitride layer. After that again we can do the metallization with the tungsten over here and aluminium copper alloy over here, right? So we can use the titanium nitride and the titanium as the adhesion and the barrier layer. And then we have the metal 3 interconnect mask, that is the mask 15. After that we are going to have the metal etch, PR strip and the metal annealing as well. So you can see we have the metal 3 layer over here. So this is how we are forming the multi-metal layer interconnection. So you can see after that we will be having the deposition of the USG and the etch-back deposition and the CMP, and this is how we will be having a perfectly planar structure of the USG over the metal 3. And then we will be using the wire 3 mask, that is the mask 16, and we are using the wire 3 etching and the PR strip, and over here we will be having the trench. In the USG layer again I am going to have the metal 4 depositions. This is how I will be having the aluminium copper deposition. Aluminium copper alloy is used as a metal 4. So after that we will be having metal 4 interconnect masks. This is the mask 17 that we have. After that we are going to etch out the metal 4 at the particular locations with the help of the mask. We are having these trenches present here in the aluminium copper alloy. Then we are going to have the passivation dielectric deposition. So the passivation dielectric deposition is done with the help of the silicon nitride. After that I am going to connect it with the bonding pad. So here I will be using a mask for that, that is the mask 18, and we are going to have the trench in the silicon nitride layer. We are going to strip of the silicon nitride and the photoresist as well for the bonding pad connection of the given aluminium copper alloy. Right, so this is how we will be having the structure, and after that I am going to connect it with the bonding pad. So these are the references. These are really amazing books which you can refer for your further studies. I hope you like this session, and if you have still any doubt, first you can refer these books. If you still have your doubts, you can put your doubts in the comment and I will be trying to resolve your doubt as soon as possible. I hope you like this session. If you like it, please push the like button, subscribe to the channel, and also do share it with your friends. Thank you so much.